This is video 18, using I/O expanders with MicroPython. The code for this video is at the GitHub site. These videos on MicroPython should work as well on any MicroPython board. All code examples have pin definitions at the beginning of the file to allow the user to alter as needed. As this channel covers multiple microcontroller solutions over time, please subscribe to stay informed and click like, as that really helps. In this video, we explore common I/O expander modules that can be easily interfaced to a microcontroller. Working with the Raspberry Pi Pico and a 5-inch LCD display left me with few pins to interface to sensors. Fortunately, the I2C pins happily integrate with many sensors with unique addresses. Most of the I/O expanders are used to interface to LED indicators. In this video, I'll use an I/O expander to interface to a keypad. Let's see a demo. I'm showing a STM32 microcontroller with MicroPython 1.24 that is wired to a PCF8575 module's I2C header. Also, I connected two multi-wire cables between the module and a 4x3 keypad. As I press the keys, the key name is displayed on the OLED and printed in Thony. Now that we know we can interface to it, let's look at the research. I found several modules at Amazon and Adafruit. I included the closest chip unit price, so each of the modules are affordable. The boards all worked with 3.3 volt power and each has 16 I/O channels, except the first board, which is the PCF8574. I chose the first three boards as they each had MicroPython drivers available. Here is a close-up of the PCF8574 module. It's sold in lots of 5 for $7, making it the cheapest module. However, it only has 8 pins. A nice feature is the jumpers to set its address and the two headers to make it easy to daisy-chain the boards. Also nice is the soldered I/O headers. Interestingly, it uses an HLF8574 chip in place of the TI PCF8574 namesake. Sadly, though, there are no mounting holes in the PCB. Here is the PCF8575 module. It's sold in lots of 5 for $13. This module has the most components. Interesting for this module is the onboard LDO regulator that converts 5 volts to 3.3 volts. The board does work with 3.3 volt power. There are two 7002 diodes that I assume are for the I2C signals. Also, there is an 8-pin 10K resistor array that is probably used with the components. All of its headers are loose and must be soldered. The main device is the Philips PCF8575 chip. The board has 4 small mounting holes. Here is the Adafruit MCP23017 module. A single board is $6. It has a power LED indicator. There is a schematic for this board, which shows the 10K pull-up resistors are on the I2C signals, the interrupt signals, and the address pins. There is nothing connected to the I/O pins, though each I/O pin is matched with a pin connected to the ground to facilitate connections to LEDs. It does have stemma, QT, or quick connectors soldered on each end, making it easy to interface to certain Adafruit or SparkFun boards and daisy-chain other modules. Here, I summarize the features of each module. This slide shows us that we can use 3.3 or 5 volt power, that we must be careful with our current usage, and importantly, there is no internal pull-down capability on any of the modules. This is important, as we will learn soon enough. Our I2C wiring is simple to connect the appropriate pins on the MCU to the module. Wiring the module to the keypad is simply just connecting a wire for each header. Since keypad types use different row-column ordering, we can define in code which pin is a row or a column. In Figure 1, the left diagram, it shows an internal view of each switch in our 4x3 matrix keypad. Each switch is connected to its corresponding row header. The other side of a switch is connected to its corresponding column header. Figure 2 shows that pressing a switch connects a specific row to a specific column. Let's look at the code for the microcontroller connected directly to the keypad. We begin by importing our I2C driver and our OLED driver, which is the SSD 1306. Then we define the pins for I2C on our microcontroller board, which are shown here. PB6 is the SCO pin, and PB7 is the SDA pin. Next, we set up the I2C device, and we set it to a frequency of 100,000 because that's what these most of the manuals say to use. Next, we set up the OLED. In this case, I've set the height to 32 so that we can see the characters easier. Next, we set up the pins for we set up the row pins on the microcontroller, and we set up the column pins on the microcontroller. And we'll see how this connects to the keypad in a second. Finally, we define a keypad matrix layout. And we're going to use this to index into this matrix so that we can determine which key we can display the value of the key that we just pressed. Here I explain the wiring of the keypad. This is a type 419 keypad from Adafruit. It's a membrane keypad which has 7 wires that come out on a ribbon cable below the keypad. The first 4 wires are the wires for the rows, and the last 3 are the wires for the column. As mentioned before, we need to set the row values as outputs, and we're going to raise their value to 1. We're going to set the column pins as inputs and pull them down to 0. So if we press one of the keys, that contact between the column, which is at 0, and the row, which is at 1, will cause the column to now read 1. And we'll know which button we actually pressed. And that occurs in this read keypad routine. Here we cycle through each row and each column, setting an individual row to 1. Later we'll lower it to 0. We set it to 1, then we check each column to see if it's 1. It's only going to be 1 if we press one of the keys on the keypad. So when we press it, we press say 5 on the keypad, that's in column 2, row 2. So row 2 is passed here in this array, column 2, and we index into this keys matrix, and we will have the value of a string value of 5, which we will then return to our main program. When we're done with that row, we return it to 0. After I've defined the class, I set this variable keypad equal to the class, defining the row pins and column pins and the key matrix that I mentioned above. In the main routine, you'll see we just loop through reading the key. If the key is not none, then we pressed it, and we have a key value which we print to the shell, or we display on the OLED, and voila. So let's run a demo. Here I pressed the key 1. Here pressed key 5. Okay, this works, but we want to use an I/O expander to reduce the pins on the MCU. First, we need a driver to translate the I2C commands to actions on the I/O expander. Fortunately, Mike Causer wrote a MicroPython driver for each of our modules. Now, let's look at the code and demonstrate with one of the I/O expander modules. Okay, let's run a demo of the keypad. I can press 1, and 1 is displayed on the OLED. Press 2, press 3, press 4, press 5. All right, we can see that it works. Let's walk through the code. All right, looking at the code, we see very similar things to the MCU-only solution, except for we've imported the PCF 8575 driver written by Mike Hauser. Next, we define the I2C just as before, using the specific I2C1 pins on the microcontroller in this case. I define the OLED. Next, we define the I/O expander device by using the driver's initialization. Most of these I/O expanders use the address 0x20, but you can change the addresses for each of the devices that you use, and you may have a value between 20 and 27. Next, we set up the wires on the I/O expander. Since we're not using the MCU, they're just numbered 0 through 7. Since on the keypad we're going to only use 7 keys, and the first 4 wires are the row wires, I set those accordingly in this array. So 0 here corresponds to this first wire, and so forth. The last 3 wires are 4, 5, and 6 for the columns. Next, we have the keys matrix, just as we had in the other routine. And now we have the class for the keypad. This is going to be slightly different than what we used on the computer. The MCU computer is capable of pull-ups and pull-downs, and these I/O modules are not capable of pull-downs. So we have to switch our logic around. In this case, we're going to figure out the intersection between the row and the column by doing the exact opposite. We will raise all the pins to 1, and when you press a pin, it will be connected to 0, and so in this case the row will read as 0. So here I'm setting all the pins to 1 by using the PCF port command to rapidly set up every single pin to 1. And then I pull down the first column to 0. And in this loop, I'm reading to see if the specific row is 0 or not. If it's not, then I return the column back to 1 and read the next column until I find the column that causes the row to reach 0. Once it does, again, I know the row and I know the column. I can put that into the keys just as before and do a lookup. Now that we have our class defined, let's run the demo. I'll press the 2 key, the 5 key, the 8 key, and the 0 key. So we didn't need any other components in order to make the keypad work. It simply needed the I/O expander. In summary, we could have added wires and resistors to the I/O expander column headers to mimic the MCU by doing pull-ups and pull-downs. However, by understanding how the keypad matrix works, we were able to code an approach that works. The next video is in progress, but I'm working several projects, so the one I finish first will be our next topic. Thank you.